It is my privilege and pleasure to introduce my good friend, Mike Stambaugh, to talk today about the most frequent historical fire regime measured, question mark, 500 years of fire scars. Mike is an associate research professor at the University of Missouri. He's the director of the Missouri Tree Ring Laboratory. His research is heavily focused on recovery and analysis of historical fire regime data in the Eastern United States as a means to inform fire and ecosystem management in the future. And Mike has shown me more than I ever thought I could know about post oaks when we got up together in Tennessee when I was at Swanee. It's a real privilege, Mike, to have you back and talking about some of your fire scar work for the Georgia Prescribed Fire Council. So you can have the floor.
All right. Okay. Thank you so much for this invitation to present this work. This is really hot off the press work. I've not actually been able to show this to many people outside of my small group before. So I hope that you enjoy this, and I hope that you are excited, and I hope that you are surprised. So today I will be talking about some of the work that we've been doing in a longleaf pine wiregrass ecosystem in southwestern Georgia. Just a brief outline of where we're going today. I'm going to talk about the background, a little bit about the purpose, mostly cover this fire history study and the data, and then leave you with some of my far out parting thoughts. This is no surprise to anyone. Longleaf pine, fire adapted, fire dependent, and here at the end of this quote by Harper, hopefully we never get to this point where without fire we can actually lose a species, which we've seen with other species already. Many experts, models agree that fire regimes of the southeastern U.S., particularly of longleaf pine, were very frequent, among the most frequent. Here we have work by Cecil Frost, work by Rich Guyette and others, and then also land fire maps, all showing historical fire frequency of anywhere from 1 to 3 years. Very, very difficult sometimes to imagine that occurring over very long time periods. Recently on Twitter, I heard someone or saw someone say that the fire regimes of the southeastern United States are the most frequent in the world. They're of a climate of productivity and fire opportunity that is really the pinnacle of fire on the planet. And this is just a map of global fire activity from MODIS. Probably not the best map to show this, but certainly see the southeast there lit up in red. Very unique for our country and potentially unique for our continent and planet. So it's a very exciting place to be doing fire history work. Unfortunately, though, this map shows the current status of fire scar records. We share some of our best records of historical fire regimes. So all these yellow dots show where fire records exist in the US and just beyond. And we have a real lack of information across the Piedmont and southeastern coastal plain. Much of Georgia, South Carolina, Alabama, Mississippi, on and on, have really no fire history data to quantify fire regimes. In a lot of states, if you don't have historical fire regime information, you're going to be faced probably with a lot of challenges of going forward with management, but not so much the case in the southeastern United States. That's pretty remarkable that despite having this lack of fire regime information long-term, it hasn't stopped the Southeast from being the leader in fire management and fire research, exemplified by all this amazing work from fire management, fire scholarship, and again, fire science. But it sure would be nice to have some historical fire information for many different reasons, right? We all know all the diversity that exists in these ecosystems. Imagine what fire history might inform us about them. or about humans and which ones were where and what they were doing, or about the relative role of lightning. Or as we go forward and the world becomes much more globally linked, how a fire fits in just broader systems, earth systems, or ecosystems. So sure, it would be nice to have more data. And that was really the objective of this study, was to establish a location where we could develop a multi-century record of fire history, and then analyze that data, particularly for fire frequency and fire seasonality, which is mainly what I'll be talking about today. So the study site here is located in southwestern Georgia. You can see that in this top center map. It's located in Baker County on the Ichauway property that is the location of the Jones Center. Here in the top right, you can see the Ichauway property outlined in yellow, showing a longleaf pine, largely forested ecosystem surrounded by heavily agricultural used landscape. The Ichauway landscape is on the Doherty Plain. It's karst topography with local relief anywhere from 90 to 200 feet above sea level. And I have been extremely lucky to be able to visit there each year from 2015 to 2018 for varied amounts of research activity. The study site is located in the northwestern part of the Ichauway property. So if you follow my pointer, the study site is located here in what's largely longleaf pine forest, some mixed pine hardwood forests, in what is called the Baker Woods. So this is a satellite image of the Baker Woods. You can see actually the boundary of Ichauway here. And then each of these kind of balloon white symbols represent the locations of 32 different longleaf pine stumps and live trees that we sampled for fire scars. This is just an image of kind of the typical conditions there in the Baker Woods. The Baker Woods is considered a little bit wetter, on the wetter end of most sites on the property. Here you can see open overstory dominated by longleaf pine. Most of these trees are early 20th century, maybe some late 19th century origin trees, where in contrast are these stumps here in the foreground that you see. Most of these stumps are of 16th to 17th century origin, so 1500s in 1600s origin. For whatever reason, the Baker Woods has an abundant, relatively abundant amount of this preserved wood compared to other parts of the property that I really just didn't see the potential to establish this work. So we were very lucky to find this, I think, here in the Baker Woods. So for the stumps, we excavated these stumps as shown here. This is digging with a shovel, getting down to the base. We clean that off so that our saw actually will work on more than one tree. And then we cut that off right above the ground level. So here we cut the stump off above ground level. You can look down on the stump here. You see the annual rings. Each of these kind of black lines and white lines and included kind of anomalies are injuries or fire scars. We then cut the second part of that stump right just below ground line. So here you have a section of the stump laying on the ground. It's GPS'd, marked and labeled for height above ground, orientation to north. And then we also take another sample out of the upper portion of the stump that we can use for dating, since the ring patterns in the near below ground wood are somewhat anomalous and can be difficult to date. And then we did a site recovery so that if you come back in the future, I think it would be very difficult to know exactly where we were. So here you have that stump placed back on the base, and then the needles and vegetation kind of recovered. So essentially, we just lowered them and kept going. Here's another image of a large section being collected from one of the stumps. we probably removed about a ton of wood, a ton of longleaf pine wood from this site. Not all those samples are from stumps. Some of them are from living trees. Here are some examples of different types of material that we were able to sample. So on the left, we have kind of a unique elevated fire scar cat face on the living trees. Some of these are critical trees to doing fire history in coastal longleaf pine. On the far right, you see a dead snag. So this, not all of the trees were stumps or living trees. Some of them were old trees that were never cut and exist today as dead snags. And then in the middle, this is kind of a spectacular piece, cultural artifact in many ways. This was not actually cut for fire history, even though it was heavily fire scarred. But here we have a cat face tree from many years of turpentine. Okay, so just a little bit about the methods. All cross sections that we collected from trees are polished so we could see all the cells in each of the rings. We measured all those rings in sequence to high precision, and then we cross-dated all the rings to the exact year using tree methods. This is the growth chronology for the Ichauway property. These samples come from all throughout the property. The growth chronology here consists of 73 different longleaf pine trees and spans the period of 1485 to 2016. So almost over a half a millennium of longleaf pine growth here. And this was published just the beginning of this year in the journal Dendrochronology, if anyone's interested. All the injuries and fire scars were identified on all the cross sections. So again, there were 32 trees here in the Ichauway property. Amazing amount of injuries. We identified over 5,500 injuries on these 32 trees. In addition, we identified a little over 700 fire scars. This project quickly kind of became much larger than I anticipated. This is about 20 times more data than we typically deal with in a fire history. And that is probably very telling about the frequency of disturbance of this ecosystem. It's not just by chance. This truly is a frequent disturbance ecosystem as identified here by just basic numbers of injuries. So for all those injuries and fire scars, we identified the year in which they occurred. We also coded each of them by their attributes. So maybe it was just a crack, and so it was coded as a crack. Maybe it also had a white resin line. So here you see kind of a white dried resin line along with that crack. Maybe we just saw disturbed tracheids. Sometimes there were just resin pockets. Many times there were obvious fire scars. So we have callus tissue, we have nice, clean mortality or, killing of the cambium right along the ring border that's nice and consistent. Here you see that in this middle image here. We have some nice response wood, kind of classic fire scars. And then on the far right, sometimes those are burned off and all you see on the profile or edge of that is a vertical crack. So each of these scars were coded so that we could keep track of the years as well as the types of fire scars that we were dealing with, since we had over 6,000 to kind of analyze and track. On top of this, we kept with our kind of standard practice that all dating and identification was independently verified. So not only did we go through this once, we went through it a second time with a second person to make sure that the dating and identification was accurate. Here's just a little look at some of the injuries that we encountered. So on the far left, here you have some disturbed tracheids, a white line, but you can see there's a small insect gallery running along the edge of the ring here. And typically that produces a very rough margin of the scar line that is not what you typically see with a fire scar that has a very clean line running along the edge of the injury. In the middle image, you can see kind of a similar effect, but this is a little higher up above a gallery. So you can see there's actually a void in this injury area. You have a rough kind of margin from cambial feeding likely. And then in some cases, we actually saw evidence of boring insects. So in this far right image, you can see a large tunnel, likely an exit tunnel, producing this scar here that's not a fire scar. And that likely hooks around lower and then reemerges back at this same surface here at the lower part of that image. So lots of injuries that are not related to fire. All the injuries and the fire scars we identified to season. So we actually gave them a seasonality within the year. We used two different classifications for that. And here they're shown on the top right. The one on the left is kind of the classic Western United States classification of fire scar seasonality based on early wood, middle early wood, late wood, early wood, and late wood position. So these allow you to determine whether or not it was maybe a spring or summer or late summer or maybe a dormant season fire scar. This has been heavily improved by Rother et al. In 2018. They kind of reformulated this for southeastern coastal plain systems. And here you see on the right a much finer resolution and classification, much more appropriate for longleaf pine. Here dividing the ring into early wood, late early wood, the transition between early wood and late wood in this zone, and then early late wood and late wood. So all this is 1 year, and each of these divisions break up the ring into different seasons. And they followed that up with here on the bottom, looking at these different scar positions within the ring and what time of year that is actually observed at these three different sites here in Florida and Georgia. So early wood, they're showing to be somewhere between February and April, move down to the middle of the ring at transition, consistently in the June month, and then late wood would be October to December. Okay, so we actually use that also for our fire scar analysis. One thing about the fire scar analysis is that there's so much data on position, so much data on year, as well as the typical techniques to do this are no longer valid with very frequent fire. So we use two methods to dating fire scars. We use compressed dating, where we assign fire scars only to the year. We give it no seasonality. We only put it in the year, okay? There are many reasons to do this. I won't go into it here, but this is what we're calling compressed dating. The other type of dating is where I call it expanded dating. So not only do we assign the calendar year, but we adjust it for seasonality. So in this example, here you might have a single ring, and let's just say it's the year 1500. Well, then depending on where the scar is in the ring, you would add these quarter increments for the year, okay? So if it's a 1500 fire scar in the spring, the year would be 1500.25. If it's in the middle of the year 1500, it would be 1500.5, and so on and so forth. So each year here is getting a much finer seasonality resolution to a quarter of a year. If the fire scar happens in the dormant season, then it just gets the year value. So in this case, it would be 1500. Okay, so I'm just going to present some basic summary statistics of what we found for fire frequency, fire seasonality, injury seasonality, and then say that some of this I can show you graphically, and some of this I can only show you statistically, because these data broke the software. The fire scar history data that actually exists will not work for longleaf pine for many reasons. It does not like multiple fires in a single calendar year, and it also doesn't like multiple seasons in multiple occurrences in a single calendar year. So we need new tools for longleaf pine. Okay, so just basic information on individual trees. The first and last fire scar recorded at the site was 1517, and the last one 2017. The number of fire scars on individual trees ranged anywhere from 0, so we did have some samples that had no scars. The fewest number of scars on a scarred tree would be 3. And then the most scars on a single tree was 108. And that tree was one of these types of trees, one of these elevated fire scar trees. This isn't the actual tree. The one that I found was a dead tree, a very long dead tree with an elevated cat face. That was just, I hate to say it, it was dumb luck for me to cut that and find that. And here are the fire scars shown on just a small portion of this tree. I have shared this around to my fire scar colleagues, and I think it is likely the most fire scarred tree ever found, period. Pretty amazing that long time. Okay, so here we're looking at a fire scar diagram for the site. And at the bottom, we have a timeline from the late 1400s all the way up to present. And then each of these horizontal lines that you're seeing are the time span of individual trees. And then each of these tick marks, these bold tick marks, represent the fire scars on the different trees. Again, there are 32 trees in this record. You can see at the bottom all the fire scars recorded on all the trees at the site. All right. Here we have from 1514, the first fire scar. We have a low sample size. We have relatively frequent fire. There's probably a fire happening every 5 years in that era, something like that. But starting here in the late 1500s, we start getting a larger sample size, somewhere around 10 trees represented. And things really pick up right around 1600, where we have extremely frequent fire all the way up to about 1870. And it's about 1870 when this forest was cut. We run out of wood, we run out of stumps, and there's a break here in our record where we have nothing recording because the forest has been cut. No trees are actually spanning that period. And then out here on the outside, we have the living forest in the fire scars on them. A couple of interesting things to point out here. You can see all the pith dates are represented by these vertical ends on these lines. You can see longleaf pine kind of continuously coming into the stand based on this, somewhat limited record of or number of trees in this record. Another interesting kind of feature in this data that we see in several other types of frequent fire systems is that right off the beginning of all these lines, you see a reduced kind of fire scar occurrence where many of these trees started off their life with relatively low fire scarring rates. Later, they may have continued with low fire scarring rates, but many of them went through very frequent burning. And here's sample 28 with the 108 fire scars over the 300 years of its life. Just that individual tree, 108 fire scars over 300 years of life, that's a fire frequency of less than 3 years on one tree. Okay, here we're adding 31 other trees because you really want to replicate these records. Not all fires are recorded on trees. There are some spectacular individuals in here. This one at the bottom is a 400-year-old longleaf pine, and we don't even have the outside. I would guess that if it wasn't rotted back, we would have another 20 or 30 years here on this individual. Okay, so just a few statistics with this. Again, this is what we call compressed fire history. So all these scars are just to the year. There's no seasonality considered in this. So this would be a very conservative fire frequency for this data analysis. For the full period of record, we have 293 different fire intervals during this record. And a mean fire interval of 1.7 years, a minimum fire interval of 1 year. I don't provide a maximum fire interval because we have in this record this period in the late 1800s without fire. It's hard to know what's going on there. I do suspect there's reduced fire frequency in that transition, and it'll be very interesting to see any of the regeneration of hardwoods and whether or not it can correspond to some of that era of forest transition. If we only look at the 1600 to 1850 period, that's a period where we have pretty good replication, pre-cutting. We're looking at a mean fire interval of 1.1 year and a minimum of 1 and a max of 5. Here at the bottom, I'm just adding this growth record of longleaf pine in what you can see during that forest kind of transition or that data break in the late 1800s to early 1900s. There's a kind of an anomalous suppression of growth that's corresponding with the trees at the site. And then you can see this extreme kind of release of the new forest kind of coming in and those trees growing under very open conditions. So there may be added information here at the stand that can help us to understand what was happening in terms of the fire regime outside of just the fire scar data. Okay, so if we actually consider fire seasonality within these years and expand these data out, not all of these fire scars are just happening at one time of year. There's varied seasonality of these fire scars. So we do have years in where we have different seasons of fire in the same year. We have a fire scar in the dormant season and then a fire scar in the late wood, or we have a fire scar in the early wood and a fire scar in the late wood. Sometimes they're on the same tree. Sometimes they're on different trees. But so that's the reason why we expanded this out to consider fire seasonality in this frequency analysis. Again, I don't know that this has been needed to be done in any other ecosystem. It really speaks to how frequent fire and how different fire regimes are here. But if we look at the full period of record, now we expanded out to having 422 fire intervals, a mean fire interval of 1 year and a minimum fire interval of 0.25 years, or maybe 4 months. And that is about the same if you just look at the 1600 to 1850 period. Here's the graph showing fire scar seasonality. So on the right, I'm showing the diagram of seasonality classifications by Rother et al. And then each of these red lines are dividing out the portions of the ring and showing what percentage of fire scars we're seeing in those different portions. And we're seeing about 50% of the fire scars happen in that transition period, which is probably more or less the month of June, thereabouts. We have about equal proportions of fire scars in the growing season before and after that transition period. Only 4% of the fire scars were identified to the dormant position or between rings. And then we had about 12% that we could not identify the season. This is a graph showing how seasonality has changed through time. And so here we have the plot from 1500 to 2000. And then each of these lines, these red lines, are distinguishing between these different positions. Okay, so we have dormant season all on this line of dots. So we have a couple dormant season fires here in the late 1500s, picking up dormant season fires here in the mid 1700s, and then quite a few dormant season fires since about 1950. The next one down would be late wood. The next one down is early late wood. And then these are the fire scars in the most common position. This is the transition position. 50% of the fire scars here really packed in here in the 1600 to 1850 period. very few late wood to transition fire scars since 1950. So a lot of this burning in the last 50 years has really been in the dormant season, according to the tree, or the early wood, according to the tree. We do have a fair proportion of the scars in the most recent 50 years that we were not able to determine what the fire scar seasonality is. But more or less, all seasonalities are represented kind of throughout time, except for in the most modern era. All right, let's just look at the injuries. So these are non-fire scars, and how do they plot out on the same diagram? So this is the same kind of fire scar history diagram. Instead of these being fire scars, these are the actual injury dates. And a couple to point out here is that you can almost tell which trees were sampled above ground versus below ground. So most of all these trees that are modern, these are all above ground. You see very few other injuries showing up on those trees. In the main set of stumps and snags, you can almost pick out which ones were sampled above ground because they have so few injuries showing up on those portions of the bowl, versus if they were sampled below ground, some of them have just a tremendous number of injuries. A total, again, of somewhere around 5,600 different injuries identified here. Again, interesting, very similar to the fire scars. We see very few injuries showing up on these trees in the earliest portions of their life. So within the first 10 to 20 years, there's a much lowered frequency of injuries on these sections of the trees. If we look at injury seasonality, so this is just like the fire scar seasonality data, but instead injuries, we see very similar patterns. So we see about 50% of the injuries occurring at that transition zone. Only a few injuries that are non-fire are showing up in the dormant season. And then again, kind of equal portions of injuries during the growing season, but on each side of that transition in the ring. This is kind of interesting that the overall activity or frequency of injuries is similar to the overall frequency and distribution for fire scars. There's just a lot of activity going on in the mid-growing season. And this is actually somewhat of a point of caution that it could be easy to confuse a fire scar versus an injury, since they're both very common in that transition period. Okay, so just to summarize here, very long and frequent fire scar records are certainly obtainable from these dead longleaf trees, stumps, snags throughout the coastal plain. Many different investigators are working on this. I think you'll see a lot more activity in the next few years, people increasingly working in longleaf pine and increasingly working on fire history in longleaf pine. Below ground sampling of longleaf pine is, I think, an excellent way to catch more fire scars. Certainly there's a lot of fire behavior and temperature and residence data, residence time data that supports that looking for fire scars on longleaf pine at the ground level will be a way to improve capturing fire scars on the species that's so resistant to fire scarring. However, the problems associated with introducing so many non-fire injuries is real, and really, I think, intensifies and slows this work. Historical fire intervals were extremely frequent. I would say shockingly frequent based on some of these analyses. It's really hard to imagine that much fire for that long. And this has nothing to do with extent. So it's hard to even think about this being widespread. 50% of the fire scars and other injuries occurred during the mid-growing season. So in that transition portion of the ring that's a critical location for both fire scarring as well as injuries. We certainly identified single calendar years with multiple fire scars. This is not the first time that this has been identified. We've seen this in longleaf pine systems in Louisiana. We've seen this in shortleaf pine systems further north into the central United States. And these data certainly are unique from a fire scar point of view. We need new methodology and potentially maybe a different way to think about these, what I call hyper-frequent fire regimes. And I just want to spend a couple minutes here better defining what I mean by hyper-frequent. Hyper, it means above and beyond, exceeding, excessively above normal. I'm defining it as the reoccurrence of discrete fire events at or near the highest frequency possible, okay? Bumping up against the constraints of fuel availability and combustion conditions, okay? And we're not saying fire over here and a fire over there and fire over here and a fire over there. We're talking about fire all on the same site. And this was brought up in some ways by Neal and Sutter in this 2010 book. Certainly there is a lot of interesting things about hyperfrequent fire that I think expand our thought process. We don't really know, I think, what the maximum burning frequency is for ecosystems. We're really good at kind of understanding how long systems can go without fire, but what is the most frequent we can burn a system if we really wanted to burn it every time as possible? What are the combinations of those treatments in terms of scheduling? Is it spring and then fall, or can it be fall and then the next spring? We know very little about how hyperfrequent fire can behave through time and space, as well as what the effects might be from burning it at this kind of extreme level. I think there are many benefits to pursuing this. Certainly it's hard to imagine. We see it in the historical record, but it's hard to imagine actually happening. And it causes us to think differently. It causes us to analyze our data differently. And it probably provides new management possibilities. So new ways to reduce risk in terms of fuels, maybe reduce emissions by keeping them low, keeping them frequent, maybe a way to provide bottlenecks against certain types of species and functional traits, such as those associated with invasive species. Maybe it's a way to reduce fire intensity in places where that's a very sensitive issue, such as dealing with issues related to timber quality. So with that, I'd like to just acknowledge the many folks at the Jones Center. My collaborator there was Seth Bigelow and Steve Jack, both who are no longer there, but provided excellent input as well as a support for this. Mark Melvin, Brandon Rutledge provided excellent orientation support for me while I was working there. Lindsay Boring actually was one of the people who initiated this work and was very much a champion, as is the current director, Keir Klepsig. I was supported by many folks here at the university, particularly Aaron Abadier helping with the fire scar data, Abby Kestermont with the measuring, and Joe Marshall with the field work and laboratory work. And most of this was supported by my my term as a visiting scientist there at the Jones Center. So I thank the Jones Center for all the support they've given me to complete this work. And with that, I'm done.
Thank you so much, Mike. This is awesome. This is fantastic. I can tell you as a prescribed fire practitioner, this kind of research really helps us inform our decisions about when to burn and how often things need to burn. So we really appreciate all the research that you do. And man, those cookies are beautiful, huh? Those are some really pretty pieces of wood. Reminds me of one of my favorite and Burner Bob's favorite quotes, and that is pyrodivers enkindles biodiversity. We got some questions from the audience. Let's see, we got a few minutes for some questions. Can you tell us if these growth rings could inform us on any other disturbance, like for example, hurricane blowdowns, or is that something that's not really applicable in that situation?
So the rings have growth information, obviously, so you can see changes in the environment due to, changes in the environment that are reflected in the changes in growth. You can also analyze the rings for changes in chemistry. So that may be actual elements in the wood or isotopes in the wood. And then any types of anatomical features. So we can now look down at the cell level and look at, in this case, impacts to the tree from injuries or fire, or actual changes in cell level features such as cell wall thickness or orientation, those types of things.
Okay, cool. Beyond just average return intervals, do you have any kind of information on proportion of the years that had those hyperfires? Or like, I think you said that the model's not dealing with multiple fires in a year very well. Is that right?
Yeah, I don't have that information on hand. I think it's fairly well distributed through time. One thing that we see in other locations that have less what I call hyper frequent fire, so more than one fire per year, is that we often see that hyper frequent fire at the beginning of European settlement. So we do have a couple places that really show maximum burning frequencies with the beginning of European settlement. In this case, I don't believe that that is the trend. I think it's much more evenly balanced through time, but check back for more information.
Cool. We got a question here about climate change. Is there any way to look at the historical fire scar data using climate change models to predict how burn intervals might change as climate changes are occurring?
I'm sorry, something popped up on my screen. That is a possibility. Probably not as much in this ecosystem. It burns so frequently that I really think of this ecosystem or fire regime in this ecosystem as kind of climate independent. So you can have wet and dry all you want, it'll still burn frequently in this ecosystem. So I really think that climate plays much less of a driver in some of the long-term fire dynamics in the Southeast than we see in places such as the West.
Yeah, other parts of the country for sure. Yeah, longleaf wiregrass is definitely my favorite thing to burn. I've even seen it burn in the rain. It's awesome. A couple people asked about why some of these old trees don't record the scars or only have just a few scars.
Longleaf, I think because it's such a high fire frequency dependent species, it has to be fire resistant. And it can be very difficult to find a fire scarred longleaf in some situations.
That makes sense, yeah.
So probably the more common situation is to sample a tree and have no fire scars than a lot. And that is one of the major challenges to doing fire history with longleaf is its extreme resistance to scarring.
Gotcha. Appreciate your work and thanks for sharing.
Okay, thanks for inviting me.